Welcome back to machine learning class. In last session, we learned the concepts and intuitions of logistic regression. Today, we're going to apply this technique to solve a real-world problem. So what we're going to do today is to apply the logistic regression to recognize handwritten digits. The data source is from this link. So now let me give you some descriptions of the data. So basically this is a image collections. Each image is one digit handwritten by someone. Collectively there are 70,000 images in total, and each image is in the size of 28 rows and 28 columns, totally 784 pixels, which are grid scaled, has a value between 0 and 255. For example, if we print out one digit, something made like this. As you can tell, this is digit 9. So somewhere is totally white, somewhere you see the ink probably a little bit dark or less dark. So that's what we get for our today's example. So let me just show you more examples to you so you get sense what the digits in the data can look like, right? Because it's written by many different people, even for the same person. If the person writes the same digit twice, 3 times, 4 times, it can be different. For humans, when we look at those digits without thinking, we can quickly identify all those digits without any problem. We do not even need to think about how we did it. We just got to know the answer right away, right? But if you want to program by certain rules, you may realize it's not that simple because the digits look kind of different. In some case, probably can be even quite challenging. So what can we do? Well, rather than specify the rules explicitly to capture all possible scenarios for each digit, we are going to rely on the particular machine learning method. Today, this one we're using is logistic regression. So let me ask you, just kind of review some concept we went over in our last session. When we are using logistic regression, is this a regression problem or this a classification problem? So if you still remember, you know this is actually indeed a classification because the target variable, the y variable, we want to clarify or we want to predict not really numerical values. Instead, there are limited numbers of categories. In our case, either digital 0 or digital 1, 2, 3, all the way up to 9. So there are only 10 potential categories the y variable can fall into. So this is a classification question. Second question, is this a binary classification or this is multi-class classification? Well, I'll already give you some clue. This, we're dealing with potential 10 categories. So this is really a multi-classification rather than binary, which only have 2 classes, either this or that. But now we're dealing with 10 potential choices as the y variable. Now let's run the program, the Python program for doing the logistic. The first block of the program is just load the data into the memory. So come here. So this is our program. It loads some dictionaries from Scikit Learn or from other packages for handling the matrix or handling the data plotting. And this one we'll talk about later. This is a predefined function which will print out, make a plot of confusion matrix. Now this is the main part of the program. And as I mentioned to you, the first block of the code is to read data in. So now let's run it. And also I'm going to use the debug mode, which will allow us to stop at a certain breakpoints, give a chance to review deeply of the variables that are in the memory at a certain point of the program's execution. So do that, click here, then click here. So we pretty much now have finished all the first code block. So what does is come here, we actually look for the data or load the data if the data is not already in our directory. So we go to the path to load the data. So that's the data loading part. Then we actually put the data into certain categories. Some are, let's see, what we load data as are this one, right? The MNIST is the main one, and this one is kind of a dictionary. Let's see. So the dictionary will have some information about the data, right? So so this gives us column name. So either we have a label column or we have a data column. And here's some description of the data. And this is the ballpark of what we need, right? This is actually the data is kind of X variables. Remember, in total, we have 70,000 images. So we're loading the 7,000 images into the memory now. So each image, even though they are 28 by 28 pixels, when the data come to here, they are actually each image got flattened. So rather than have two-dimensional data to represent the image, the data only have one dimension, but has all the way up to 784 digit, right? Because this index start with 0. So totally on each row we have 484 numbers. Because those numbers really indicate the darkness level of the each image. And if we scroll down vertically, we'll see there's a lot of those. Actually, there's a 70,000 images as X variable. So the Y variable, or the target variable, it also has 70,000, and this Y variable tells us associated with each image is that 0, 1, 2, 3, 4, 5, 8, 9, right? Tells us what the label or what the Y variable corresponding to each image data, which is X variable in our case. So then there are also some lines of code which print out the data dimension. And one thing I want to mention here is this particular line of code will do the data splitting. Since we totally have 70,000 data, we actually make 1/7 of that as test data, the other 6/7 as our train data. So we split data in that way. So we'll have both training and testing data. And here a few lines of code just print out dimension of the images and the training data or training label or the test data or test label. And then lastly, we just print out some random samples from the training set and give a sense what the data, what the images look like. And for your convenience, I also copy them into here. So So we actually did those things. We run the code, download the image database, and the code split the images to 60,000 as train images and 10,000 as test images. And we also have some quick review of some variables, which kind of stored as kind of memory of the ID, the spider ID. And this is just a few examples of what the images look like in the training data set. So now let's go further. Okay, after data have been loaded, right, we can now run our code to train a logistic regression model. So that is the second block of our code. And the key part of this code actually just 3 lines. The first line is we create an logistic regression class instance. To do that, we need to specify multi-class as a value of multinomial, and we pick a solver which will give us the optimization of the coefficients, right? So we're choosing this LBFGS as the solver. One thing is worth mentioning is, again, this is a multi-class problem, right? As I also mentioned in previous session, when we have multi-class logistic regression problem, we have 2 ways to deal with it. One way is we can build multiple binary uh, logistic regression. In the end, we combine the multiple binaries and make it become multi-class classification, right? So if we do not specify this multi-class parameter with this specific value, the Scikit Learn default behavior is to build multiple binary logistic regression, right? But since if we do that, it works, but it takes actually much longer time to do it. And now we are, in our example, we're going to ask for a multinomial um, logistic regression. Essentially, what does that do is, also we mentioned that in last session, what that do is the algorithm basically replace the logistic function or so-called um, sigmoid function into something called the softmax function, which will be able to deal with the classification across multiple categories at the same time. So this line you should be like know a little bit better. So the second line is very simple. We just plug in the x variable, the train image, and the y variable train label, which we split in the first code block. Then once we have that, the model is trained, we're just going to run the prediction on the test image, right? And this prediction will be the corresponding labels or y variables associated with those test images. Now let's go to the program to run it. All right, let's hit the run button again. So now the second block of the code is being invoked already. Actually solving this problem may take a little bit time. Let's just wait here patiently. Still working on it. Okay, still working on it. All right, it's done, right? We actually finished the work with the model training and prediction with the logistic regression function of Scikit Learn. Let's take a look. Okay, maybe go back to the code, right? Let's look again. Yeah, this is a code block, just as I showed you. these 3 lines are the key. Create instance of the logistic regression or Scikit Learn, then put the train data in x variable, y variable, and later we do the prediction for the test image. And the rest part of just doing some plotting, showing some outcome from the classification using the testing data. All right. So, and after we doing the training and do the testing, and here just print out some misclassifications by the logistic regression. This one, the actual value is 2, the prediction is 8. There's some other similar examples. Basically, there are some mistakes or misclassifications by the algorithm. But overall, how good is the algorithm? Well, to describe how good the algorithm is for classification question, we often use one metric called accuracy. It's very easy to understand the meaning of accuracy. Basically, the denominator is just the total number of predictions that we have done. In our case, remember we have 10,000 images in the test data set. So the denominator in our case is 10,000. And the number of correct predictions is the numerator. So basically this just tells us percentage-wise what percentage of our prediction is correct, or what percentage of our predictions is lined up with actual. So it reported as 91.94% by our method, right? Let's look at the code, and as we can see, it's 91.94, right? It's not bad. We only have 3 lines of code, and which give us 91.94%, dealing with all potential and possible handwritten digit. So accuracy is one way to show how good our classification is. Another metric is also very useful. It's called confusion matrix. So how to read it? Well, now rather than get a simple percentage of the accuracy, we actually got more information, right? Here is the confusion matrix. So vertically, there are labels of actual labels for those images in our test data. And horizontally, we have the prediction label, right? Given each test image, what's the prediction based on our logistic regression? So the way to read it is, if you see the numbers on the diagonal, just means the actual and the prediction are consistent. So that means every number on the diagonal line indicating we have them predicted correctly. So that's good. And for things which are not on the diagonal line, they are misclassification. For instance, if the actual value is 0, well, there's 5 instances where our prediction says is 2, right? There are 5 cases which got wrong for the actual value of 0. And also there are 4 instances where the actual is 0, but our prediction says it's 3. And now I think you get it, right? In this case, there are 10 cases, 0 have been misclassified as 5, right? So let's pick another row. The actual value is 5. Now we get about 38 cases. The prediction says is 3, right? Based on this, we get actually kind of more information about how our prediction performs versus the actuals. And you can imagine if we add up all the numbers in the matrix, in the square, it should add up to 10,000, because in total we have 10,000 samples in our test data set. And if you add up all those ones diagonally, the sum of diagonal numbers, those are the correct predictions, right? So if I have the sum of diagonal divided by sum of everything in the square, that also gives us the accuracy rate that we have just seen on the previous page. So eventually, this confusion matrix just give you more information, not only tell you one final number in terms of accuracy, also tells you in which case the model performs, in which case the model mispredict. So now let's move on to the next block. Well, as always, right, we also mentioned in the last session, we can also use the gradient descent approach, the gradient descent classifier to deal with the kind of logistic regression problem, right? So what do we need to do is also we need to 3 lines of code, right? In this case, we need to invoke SGD, which is stochastic gradient descent classifier in Scikit Learn. Now for that, we need to, since this is a gradient descent approach, we need to have a few more hyperparameters. Among all the things, the most critical variable or the parameter or argument we need to put in is we need to specify the loss function as log. So this will give us some equivalent to the logistic regression, the previous method we used, because the SGD classifiers indeed also support other type of classification. To make it equivalent to the logistic regression, we had to specify the loss function is log. And there are some other hyperparameters that may need some certain optimization. But anyway, among all those things, this is the most critical. So this line kind of is creating an instance of the HGD classifier of the Scikit Learn. And this line you are familiar with, right? Once that instance is created, we can put the train data and train label into it. Then with that, we can plug in the test image for predictions on the testing data set. And here again, there are a few images of where we misclassified with this second approach. Now, let's also go back to the code, right? Let's continue to run the code, the last block of the code, get the SGD classifier work. So now the third block has been triggered, and it's also going to take a little bit of time to run through. Let's just wait patiently. All right, it's done. So everything is done. So with this one, let's see. I also copy the result into the slides for your convenience, right? So with this guy, we see there are some misclassifications. And then accuracy, same definition. And with this method, we achieved accuracy of 89%. Is slightly lower than the 91% we achieved with the logistic regression. Now let's examine the confusion matrix, right? Same idea. It just tells you where the prediction is consistent with actual or where the prediction inconsistent with actual. Overall, if we go back a few pages, you will see that it's consistent with the accuracy comparison the confusion matrix is diagonal, also showing slightly lower number compared to what we achieved with the logistic regression method in the scikit-learn. So this so far pretty much concludes the example running the code to train and predict to get a sense of performance of the classifier, actually two classifiers, the logistic regression and the SGD classifier equivalent of the logistic regression with the scikit-learn. So now we probably have a few questions to think about, right? The first question is, as I mentioned to you, the accuracy of the SGD classifier is slightly worse than that of the logistic regression. So why is that? Well, the SGD classifier is using the gradient descent approach, for which we have quite a few hyperparameters to provide. So part of the reason of that is there's certain need to search the optimal hyperparameter to achieve the maximum result, the best result from the SGD classifier. That's one thing. The other thing is with the gradient descent approach, particularly the stochastic version of it, there's a little bit of randomness because this SGD classifier works is tune the coefficients by observations by each train samples. So it's not getting like the way that logistic regression does, which is take all the data. There's no sampling, there's no sequence, there's no dependency on which data get into training first or second. So there's a little bit of noise or the uncertainty with the SGD classifier. Considering the two reasons, additional hyperparameters to optimize, and also considering the nature of stochastic gradient descent approach, it may get noisy, and the optimization it gets can be really close to global optimization, but not guaranteed is exactly same as the global optimization. So that's why the SGD classifier is providing a result slightly worse than the logistic regression approach. Well, the second question is, what are the advantages and disadvantages of SGD classifier versus the logistic regression? The previous discussion, when I answered the first question, I pretty much already discussed the disadvantages of SGD classifier versus the logistic regression approach. Well, where you see the true benefit of the SGD classifier is when the data is really big, right? Because for logistic regression, it's a batch mode. It takes all the inputs, all the training samples, and optimize the whole thing as a batch mode. But when the data becomes big, let's say not 60,000 anymore, becomes 6 million or 60 million, it's going to explode the memory capacity, probably for many computers. In that case, the SGD classifier is the approach you must take in order to handle a really huge data size. So that's the main advantage of the SGD classifier, which can handle really big data, for which the logistic regression, the batch mode, may not. Later in this course, we're also going to learn some more advanced machine learning methods. With those methods, we can easily achieve an accuracy rate of 98 or 99% on the same digit recognition problem. So why they are much better than the logistic regression approach? Well, think about this. logistic regression, or its equivalent SGD classifier, basically look at all the pixels within the image and determines kind of each pixel on its own, whether it should be white or black or some kind of gray at certain locations, pixel by pixel, to establish its relationship with the label, the y variable, what the number is, what category is, right? So even with that very simple approach, we can get a decent recognition accuracy of 91%. But the main drawback of this approach is, again, is kind of considering all the pixels, the darkness, the ink darkness on their own, right, in isolation without considering the neighboring pixels or the kind of interactions across the pixels. Because think about this, what makes 8, what makes 7, or whatever number digits is not just about certain pixel at certain location. It's also about the other pixels around this particular locations, whether you got the your inks one by one very closely, or you may get the ink at this direction versus get the ink at the other direction. So that kind of, if you consider interaction, consider relationships across the pixels at the multiple locations, that has a lot of good information to improve the accuracy of the algorithm. So that's why other more advanced approaches, machine learning approaches, can achieve much better accuracy rate than the logistic regression we're doing today. Anyway, even with this very simple approach, we are having an accuracy rate about 91%. That's not bad. Well, that's all for today's class.